The complex curves on Pearl River test the team like never before.
因为它外形比较复杂，应该也是算得上。
Because of its complex shape, there's a great variety of facade units.
这个加工这个难度，
So the difficulty in manufacturing increases tenfold.
上百倍的增加，那工作量也是很多的。
The tower has 7 types of windows and 6,000 panels in total. On the factory floor, 3 production lines and 300 employees work solely on Pearl River. 1,900 tons of aluminium will go into making the window frames for the Pearl River Tower. This will be the largest window curtain of its kind. The panels are some of the biggest ever seen. The largest, at 24 square meters, is more than 3 times the size of a panel on a conventional high-rise. In all, Pearl River will be cloaked in 80,000 square meters of low-E glass, enough to cover 10 soccer fields. But all that glass opens a window for trouble. Water, one of any building's worst enemies. Southern China gets up to 12 typhoons each year. April brings the monsoon season to Guangdong province. For half the year, more than 150 millimeters of rain falls on Guangzhou every month.
很大的挑战，因为它是外倾斜、内倾斜并。
We have to ensure that the curved surface is watertight, both inside and out.
防水的这个要求非常高。
With its reputation at stake, Zhonghe undertakes its own testing of the window curtain at the Canton Quality Control Station in Guangzhou City. This giant section of window curtain will endure more intense wind and rain over the next 2 days than the building might expect in its entire lifetime. Architect Russell Gilchrist of Skidmore's and local architect Huang Huijing will observe the testing firsthand. In the wind test, pressure sensors placed inside the facade will measure the distortion of the glass. A large pump inside the glass cavity simulates high winds by sucking in air, causing a buildup of negative pressure. The facade is battered by winds 1.5 times higher than the worst winds ever recorded in Guangzhou. Wind pressure can open gaps for water. So does the glass remain watertight? Turn on the typhoon.
All facade projects in this country are subject to this kind of test. But since it's the first time a double facade is being used in this climate, this test is a first in our region.
The interesting bit will be when they turn on the fan, because that will actually simulate horizontal wind and rain together. And that's where we test all the little gaskets to make sure that everything is watertight.
The fan simulates winds of 144 kilometers per hour. Outside the facade, technicians check for damage on the rubber gaskets. And on the inside, Russell is delighted to find it's bone dry.
I think we're good. That's a good test. If you get weather like this, that was a good test for it to pass.
Good thing rain can't get in, because the architects have set the tower directly into the prevailing winds to harness their power. Facing Pearl River directly into the wind is a bold move.
Now, that's a little counterintuitive, because in a super tall building, you're trying to reduce the wind load on the building. And most people would tell you that it is unwise to face the broad face of the building directly into the wind, because the sail effect on that building is tremendous.
The prevailing wind that comes from the south 10 months of the year will hit the tower head on. The wind will funnel through 4 wind holes, located 1/3 and 2/3 of the way up the building. Dr. Sui and colleague Mr. Wang check out the bottom 2 wind holes.
Do you feel the wind on this side? Once the glass facade is in place, the wind power will be greatly enhanced. There'll be an aerodynamic tunnel.
Wind tunnel testing undertaken in Canada reveals the wind speed through the holes will accelerate up to 2.5 times.
I think most people would understand that if you narrow down a funnel, it's going to accelerate whatever you're putting through it, especially if it's symmetrically shaped. But I didn't know it was going to be 2.5 times.
Their next challenge, finding wind turbines that are up to the job. Wind turbines like these are sprouting across the globe, but they can only cope with wind from a single direction and won't work in a turbulent cityscape where gusts of wind can come from all sides. The answer? Vertical turbines. They spin no matter the direction of the wind. Best of all, they cope with the turbulence common in the city.
In other buildings, the wind turbines are commonly placed at the top or on an open platform.
But in a radical move, Pearl River's turbines are the first in the world to be integrated within a building, with each of the 4 wind holes housing 1 vertical turbine. It's revolutionary thinking, but it rattles the engineers' nerves.
People are concerned that vibration will be a problem when the turbines start working here.
The noise and vibration could do more than annoy the occupants. If the vibration mirrors the natural frequency of the floors, then the effect will be amplified, causing structural damage. The architects decide to commission a test at Hunan University, known for its elite engineering department. Engineers use a 1:150 scale model of the tower, complete with its own mini turbines. Inside the wind tunnel, they subject Pearl River to high winds, measuring wind pressure across the entire surface of the tower. Taking their wind pressure readings, they calculate the vibration of the wind turbines and compare it to the natural frequency of the floors. They conclude that the vibration of the turbines will not vibrate the surrounding floors. For the engineers, no vibration means good vibrations. Not only will the tower harness the wind to make energy, the wind holes will negate a potential hazard. Wind pushes hard on the side of any super tall structure, and in extreme weather, this same energy can cause vortices to develop on the opposite side of the building, pushing back the other way. These opposing forces can build up so much that the building begins to sway. But on Pearl River, the wind holes act as pressure relief vents, reducing the pressure on the building by about 1/3.
And in a super tall building, that's a tremendous amount of reduction because it helps you to reduce the acceleration of the building and make the building more stable.
By reducing pressure, the wind holes not only make the tower stronger, but there are cost savings too.
So we need less steel and we need less concrete to help the building stand up, and that, of course, is a very sustainable thing to do.
It's also sustainable to harness the power of the sun. Photovoltaic panels will cover most of the east and west sides of the tower and the domed roof. Photovoltaic, or PV panels, take light energy from the sun and convert it directly into electricity, which feeds straight into the building's power grid.